In the quantum field theory, the renormalization is a very important one when we consider the loop diagram. And today I will talk about the renormalizations of the quantum electrodynamics, QED, starting from the counterterm by considering the older loop diagram and how the coupling constants runs over the energy scale. So the QED Lagrangian can be written by the following term. The first one corresponds to the kinetic term of the gauge boson, which is written by the Beer-Strunz F mu. And the second term corresponds to the Lagrangian. The psi represents the spin 1/2. And the d mu, the covariant derivatives contains the gauge interaction term between the gauge field and the spinor field. And we want make the renormalization for this QED. So the older field and the coupling mass are renormalized. So gauge fields are renormalized, and spinor field electric charge, which correspond to the coupling inserted in the covariant derivatives and the mass term. Here the chart represents the renormalization constant, like just 3 and just 2 for the wave function, just E for the electric charge, and just M for the mass. And one can decompose this renormalization constant with the Bayer term and the counterterm part. So by inserting that this renormalized quantity into the Bayer Lagrangian, now we can decompose to the Bayer term and the counterterm part. So for example, if we insert the I0 here, then now there is the renormalized part and the counterterm part. And for the renormalized parts of the Lagrangian had the same structure through with the original Bayer term. But now the older term becomes a finite because the infinite divergent parts are all absorbed in the counterterm. Now there are for counterterm delta 3, delta 2, delta m, delta 1, and here the covariant derivatives, which includes the gauge interaction term, the combinations of the jet E and the jet 2 from spinor field and jet 3 coming from the gauge field gives the counterterm for delta 1. And this counterterm absorbs all the UV divergence arising from the loop diagram. So now we will determine the counterterm by evaluating the loop diagram. The first example is the photon self-energy, also called a vacuum polarization. We'll use the dimensional regularization, so that now the space-time dimensions are set to be the small d, and its deviations are denoted by the epsilon from the four-dimensional space-time. The photon self-energy can be drawn like the following form, and by the Biermann rule we can evaluate the loop diagram amplitude. So here there are two Fermion propagator. This gives this internal line, and the vortex gives the electric charges times the gamma matrix. And because now we are in the dimensional regularization, the momentum integrals given by the d to the dk, and the electric charges that has now the dimension in the d-dimension space-time. So to make the dimensionless coupling, there is scale factors will be multiplied by the power of the epsilon, whereas epsilon already I mentioned it represents the differences of the dimension. And by extracting the Lorentz factors, then the only remaining one is the divergent part. And by using the Buyman identity and defining the loop momentum and the integrations of this loop momentum, and by using the dimensional regularization, one can obtain this capital pi, and the divergence part appears as one of the epsilon, because we will go to the epsilon go to the zero limits, so that the dimension becomes a 4. So to remove this divergence, which is appears this photon self on the diagram, one can determine the counter term. The photon field counter terms was there is a delta 3, and corresponding to this counter term, one can consider that the counter term contribution for the photon self energy. Lorentz structures are the same. The difference was just a delta 3. And for the MS bar scheme, the delta 3, the counter terms cancel the older term 1 over the epsilon minus the gamma e, which is all constant, plus ln for pi. So the one can determine the counter terms delta 3 for the photon field in the MS bar scheme in the following form. Then this delta 3 cancel this divergence, this part. Now I turn to the second example, the electron self-energy. This renormalized mass term, so we can determine the delta 2 and delta m, these two counter terms. The electron self-energy in the one loop diagram can be drawn like the following form. Now here is the one photon and the one fermions in the internal line. So the corresponding propagators are following for the fermion and for the photon. Also, there are also gamma matrix for the vertex, and similarly for the dimensionless coupling, there is a mu factors with the epsilon powers are inserted. Also, one can decompose this self-energy with the general Lorentz structure. This one loop self-energy can be decomposed with the peak cancel, which represents the contraction between the momentum and gamma matrix and the mass term. So by evaluating the integrations with the dimensional regularization, one can extract the UV divergent part. Similarly, there's one of the epsilon. We will go to the epsilon, go to the zero limit, and the finite part is that not constant. And this divergent part can be offset by the some proper counter term of the delta T and delta M. So to remove the divergence, these counter terms delta T and delta M gives the following contributions for the electron self-energy. So to cancel the UV divergence, delta 2 and delta M are determined. Now we know that there is this can be P cancel term can be offset by delta 2, and the mass term can be offset by the delta M. So in the MS bar or MS scheme, delta 2 and the delta M are determined. Lastly, now we'll turn to the vertex function, which is renormalized charges. So this determines the counter term finally remaining one delta 1. In the one loop level, the vertex function can be drawn like the following diagram, and the 1pi or one loop vertex function can be decomposed in the following Lorentz structures. And in this diagram, there is the two fermion propagators and one photon propagator. So here is photons, and this is for the fermion. And similarly, there are voltax with the three part. So this gives the electric charges and the three gamma matrix. Similarly, we can obtain the divergent part by evaluating the disintegration. The divergent part also represented by the one of the epsilon in the dimension regularization. We will take the epsilon go to the zero limit. And as similarly seems the counter term delta 1 now the contributes the additional voltax here, and this will obsess the divergence coming from the loop diagram. In the MS or MS bar scheme, now the delta 1s are determined. And one can find that this delta 1 from the voltax function and the delta 2 comes from the electron thermogenesis are the same. But this is not coincidence. This comes from the Awad-Takashi identity or briefly Wad identity. At the one loop, we bounds that the counter term of the delta 1 and delta 2 are the same. But these results are all unsure for the every loop level. And we thought the Z1s are determined by the combinations of the other renormalization constant, ZE, Z2, and Z3 sort of the one half. And now we know that Z1 and Z2 are the same, so the ZE and the Z3 are now also related. This means that the electric charges renormalizations are fully determined by the photon field renormalization in the QED. So now we know that all the counter terms are determined to cancel all the divergent terms which is arising from the loop diagram. Then how can we use this counter term? We can determine the energy equation by using the counter term. The Bell couplings are the scale independence. So that if one differentiates this Bell coupling over the another scale, this is equal to the 0. But this Bell coupling can be decomposed with the renormalized coupling and the renormalized constant and some dimension part. So the differentiations are now decomposed. And this is the starting points of the Kallan-Thalmont equation or the RG equation. One can define the binary term as a beta function. The beta function represents the differential equations for the renormalized coupling E. So the solution of this beta function gives the learning coupling over the another scale. And because we will take the epsilon go to 0 limit, so that the first term will be disappear, and we know that in the QED that is related to Z3. So and by using the results of the counter term, then we can obtain the beta function by using this Kallan-Thalmont equation. So the beta functions of one loops are given by the E cubes over the tau pi scale. For convenience, one can define the bind structure constant, which is the dimensionless quantity, as electric charge scale of the ball pi. For this bind structure constant, we can bind the beta functions for this alpha, and by solving this differential equation, the beta function, the solution of this gives the learning coupling. So the electric charge or electric coupling in the QED runs over the energy scale. It increases with the logarithm behavior, and at the specific energy scale, it goes to the diverse. This is called the lambda pole of the QED. Now we know that the electric coupling of the QED cell runs over the energy scale. This is called the learning coupling, which is a result of the renormalization. And I will turn to the how the photon propagates corrects the vacuum polarization. This is a different approach to get the learning coupling with some more intuition and the qualitative explanation. So actually the photon propagators contains all the loop diagram. And one can define the 1pi diagram, which is represents one particle irreducible. And this 1pi diagram can be decomposed with the Lorentz structures. And we will sum over all the 1pi diagram. And this gives a geometric series. So this gives the 1 over the 1 minus capital pi. And in the numerators, this corresponds to the just Lorentz structure. So basically the factors of the 1 minus capital pi screen the electric charges. So if there is some electric charges, and around of these charges, there are vacuum, and the vacuums produce generalize the virtual particle, like as electric dipole. And this screen the effects of the electric charges of the center. So this makes the potential get the behaviors like the 1 over the R as a Coulomb potential. And this modifies the propagators with the replacing sort of the Weyl coupling to the scale dependent refractive coupling. One can obtain such a potential form by the Fourier transformations with the Born approximation, but such a here's this scale dependent refractive coupling now becomes the learning coupling constants of the QED. When the momentum scale is larger than the mass scale, it shows that the logarithm behavior, which is a consistency with learning coupling constants with the Rg equation. Now we'll turn to the how this normalization can change the mass. The mass normalizations appears from the electrons of energy. Similarly, one can obtain the 1pi diagram for the electron. And here now we can define the two different mass for the electron. The physical mass, also called the pole mass, is defined by the locations of the pole of the full propagator. So now all the 1pi diagrams are summed over, so this gives the geometric series again. So now the 1pi self energy, capital sigma is located in the denominator. And to make the vanishing denominator is equal to 0, so one can define the pole mass, which is represented as inverse is equal to the 0. This corresponds to the pole. At the one loop order, is just the same with the pole minus minus p cancel sigma v sigma s equal to the 0. and poles are determined in the following form. And there are two different renormalization schemes. For the on-shell scheme, the renormalized mass is the same with the physical pole mass. So in these schemes, the counter terms are determined to make the renormalized mass to be the same with the physical pole mass. So for the counter term contribution, the on-cell mass renormalization scheme fix the delta m to make the same m and m pole value. And second on-cell conditions that comes from the largest of the propagator, which is to mean that if we differentiate the inverse of the propagator, we can obtain the residue, and we require that this residue is equal to the just a unit 1 or just a I, and this determines the remaining counter term delta 2. Lastly, the remaining part is the Bertax function. This Bertax function changes the anomalous magnetic moment. One can decompose the Bertax functions in the two Lorentz structures gamma mu and sigma minus q nu. These structures can obtain from the some several identities, and the functions lattice with each terms called form factors. And these form factors that change some observable like as a magnetic moment. Especially the up to gives some contribution for the magnetic moments of the electron, and one can obtain the anomalous magnetic moments in the one Lip's level, which is the order of the structure constant. So today we talk about the QED renormalization, starting from the counter term to cancel the divergence. Then all the counter terms can be determined by the loop diagram of the photon self energy, electron self energies, and the Bertax function. And we turn to the how these determined counter terms can be used. For the coupling, we use the Cauchy-Riemann equations to obtain the beta function, and by solving the beta function, so we can know that the learning coupling behaviors of the QED with the logarithm scaling, and also the for the electron propagators, this gives the effective mass, and one can define the normalized mass is the same with the physical mass in the on-cell scheme. Lastly, the Bertax functions that determine the form factors which affect the anomalous magnetic moments of the electron.